So we talked about the Atlas and we talked about the IBM System 360, bringing in many features of modern assembly language programming that we're used to today. The other two that I want to talk about are the CDC 6600 and the PDP-11. The CDC 6600 introduced an idea that we now call superscalar, which they called parallel by function. And what this is a recognition that because you're executing multiple instructions at once via pipelining, you could do a bunch of different things at the same time. So when you are adding two numbers together, you're not multiplying two numbers together. And so in a regular pipeline system, you have to say, I'm going to add these numbers together, and then the multiply unit just doesn't do anything. It's wasted effort in that moment, right? And so what they did is they split up these functional units. In this case, they had an add, multiply, a couple of multiply units, divide, long addition, shifting, Boolean functions, incrementing, as well as branching. And each of these could happen at the same time. In order to actually deploy this, they built a larger register set and had the register set able to access, put information to any of these different kind of these different functional units, and then have them operate one at a time. The question then becomes, how do you allocate these resources? When an instruction comes in, how do you decide where it's going to go? How do you decide what registers it's going to access? How do you decide whether things are ready and it's going to wait? The machine has to do all of this for us. And so CDC 6600 also deployed a thing they called the scoreboard, which is the instruction reorder, issue, and retire. So as an instruction comes in, it's going to look at the resources that the instruction needs, right? The registers that it needs, the functional unit that it needs. It's going to look at what is currently running in these functional units as the pipelines are trucking through. And it's going to say, yes, this can be deployed right now, this can be issued into the pipeline right now, or no, this has got to wait for this result, or it's got to wait for this functional unit, right? So as each instruction is loaded, the scoreboard considers the resources required, and then deploys that instruction to the functional unit. This is also a recognition that different instruction functional units are going to take different amounts of time to execute. The addition functional unit takes only 3 cycles, whereas floating point multiply took 10 cycles, and floating point divide in this implementation took 29 clock cycles to execute. And this is why it's important to be able to, while that floating point divide is happening, be able to issue multiple instructions to the add functional unit that can be completed over and over again. And so the scoreboard has to be able to have lots of instructions available to it that it can deploy in the right functional units so as to not waste time. This is the other big advantage, or the other big advance of the CDC 6600 was what we today would call a register ISA, but they would call register operations. And so what they did is, we're not going to do anything in the memory. We're going to bring everything into registers, and we're going to have registers be the operational unit. And this seems natural today, but it is true that other machines, even today, have this idea that you can actually operate on a area of memory instead of just restricting your operation to registers. As the speed difference between registers and memory grew, there was this sort of push and pull, right? One set of priorities say, let's abandon memory as a place to do any work, and then just optimize the movement of information from memory into registers. And then the other way of thinking is, no, we still have to be able to have memory do work, because that way we can offload some processes to the memory that could do the work itself, right? So offboarding functional units, things like this, it became a sort of difference of development. Anyway, in order to implement all of these different functional units, the CDC 6600 had an instruction stack, what we would today call an L1 instruction cache. Basically, you would load instructions in from memory, load instructions in from memory, and then you would have access to them much faster than you would if you had to load them one at a time. So you'd load them into memory, and as they get issued, the stack would move up and the next instruction would be ready to issue. So you could have multiple instructions issued at the same time. The scoreboard would be able to say, this instruction uses these registers and this functional unit, and this instruction uses these registers and this functional unit, so let's deploy them at the same time, right? So the instructions cache combined with the multiple functional unit allowed this idea of superscalar processing, which is what we would talk about it today. And then the last machine to look at is the PDP-11. This machine, and there's a link as well. I don't have pictures of these machines. I probably should have brought them in. But this machine really cemented many of the features that we look at today in terms of modern assembly language in a reduced instruction set capacity compared to a complex instruction set capacity. One of the big features was what we call an orthogonal instruction set. And that means that all registers can operate on all instructions can operate on any register, and all registers can be used in the same way by all instructions. This was, again, a somewhat unusual suggestion because there was this idea that special purpose registers could be used for special functions. If you had a register that was optimized for accumulation or indexing or something like that, then you want that to be the register you use for indexing. PDP-11 said, no, we're going to have every register can do anything, right? So you can index on this register, you can increment on this register. And in fact, the idea that the program counter is just another register like any other, also initiated here in the PDP-11. This is a somewhat unusual development because in previous versions of machines, keeping the program counter separate had the same motivation as keeping status registers separate, keeping vector tables separate, keeping this stuff away from the programmer so they couldn't make any mistakes. But as programming developed, as people got more comfortable with assembly code and there were compilers and various other things sort of between the programmer and the operation, there was a recognition that being able to do things to the program counter would be a good idea. Being able to add to the program counter in the same way that you can add to a register when you are indexing, this is going to be valuable. It's going to make branches and jumps a lot more efficient, and it's going to broaden the number of things you can do with program control flow. So program counter was a general purpose register. It also implemented a broad set of addressing modes, and this is a thing that today is a little bit of a difference of opinion as well. It gave you lots of different things you could do with addressing modes, which is to say, how do you find the information you're interested in? Either it's in the instruction itself, right, immediate addressing, or it is in memory in a location specified by an instruction. That's direct addressing. Or it's in a register specified by an instruction, right? That's register addressing. Or it's in a memory location that is specified by a register that's specified by the instruction. This is register indirect addressing. So we'll talk about all the different addressing modes later on, but the PDP-11 gave these addressing modes lots more flexibility and lots more power. And today we have machines like ARM that implements many really interesting, complicated addressing modes, auto-indexing addressing modes. Compared to RISC-V that really simplifies the addressing modes and says you can do it exactly one way, and then all of the other features need to be implemented in code rather than in hardware. And again, another sort of diversity of opinions when it comes to what is the best way to make these things work efficiently and in a regular way. PDP-11 also gave us priority modes. Again, there were priority modes in the past, but this established a large collection of well-predictable priority modes that allowed operating systems and low levels and high levels and interrupts and a bunch of other stuff. Memory mapped I/O, again, we mentioned it earlier in an earlier machine, but this really brought it into the programmer realm so that you could access input and output in the same way that you would access locations in memory, using the same registers and the same instructions. So it really solidified this idea that we want an instruction set to be consistent, because when it's consistent, we can optimize it. We can make things a lot faster and a lot better. So that is the beginning of some of the standard things that we do today, right? Pipelining and superscalar and memory mapped I/O and priority modes and a bunch of other stuff. And where these things came from, even in the 1960s and 1970s, which feels like a long, long time ago today. And computers today are so much more advanced than these machines back then, but we're all more or less doing the same thing.